Hi, I'm Artavas Tkhachaturian, an aspiring engineering student specializing in transportation from Armenia. For my individual project of the computer-aided design course, I chose option B, the educational mechanical model. Civil engineering students often struggle to intuit how invisible forces travel through complex structures, such as bridges. We know formulas, but we rarely see and imagine the mechanics. My objective was to create a virtual laboratory inside SolidWorks to assist students in this problem. Instead of just modeling one bridge, I modeled 4 distinct types of bridges: a beam, a Howe Truss, a tack arch, and a suspension, to visually demonstrate how different geometries manage the same gravity load. My goal is to determine which of these structures is the most efficient for given constraints. To make this a scientifically valid comparison, I had to treat this like a lab experiment. So I established strict control variables. First, every bridge features a standard 20-meter reinforced concrete deck. Second, every bridge uses the same material, A36 structural steel. And third, every bridge is subjected to the exact same load, 100 kilonewtons applied along the center of the deck. I started with the beam bridge as the baseline. As you can see from this smile curve, it relies purely on bending stiffness. It deflected over 23 millimeters. The beam bridge is simple. It relies only on 3 I-beams, but is mechanically inefficient. So I went on for searching more efficient structures, and I started to model an arch bridge. And the most interesting educational moment occurred here, during the design of the arch bridge. My initial design used very thin vertical columns to connect the arch to the deck. Theoretically, the geometry here was perfect. But when I ran the simulation, the bridge, as you can see here, it just collapsed. And you can see here that the vertical columns aren't just compressing, they are bowing out in an S shape. So, as I figured it out, this is a classic example of Euler buckling. The members were simply too thin to handle the given load. So this is an excellent case study for students, and this was an excellent case study for me, demonstrating that geometric theory must always be validated by stability analysis. To fix this, I replaced the rods with heavy square tubes, or put it differently, I made the structural members thicker. Of course, this solved the buckling and created the stiffest bridge of the group. This bridge deflected only 1.78 millimeters. But there was a trade-off. These thick structural members increased the mass of the whole bridge to over 5,300 kilograms. The beam bridge was 1,300 kilograms. So this was a brute force solution. Okay, so I went on for a more efficient structure, and I stopped on the Howe Truss. This simulation perfectly visualizes the force flow. If you look at the color plot, the green diagonals are in compression, and the red verticals are in tension, as given in theory. This triangulation allows the structure to be rigid without being heavy. So, when we compare the numbers, the difference is significant. The arch, it was the stiffest, but it weighed 5,300 kilograms. This truss bridge weighs only 2,000 kilograms, less than half the mass, but it still kept the deflection to just about 4 millimeters. And by analyzing the specific efficiency metric, which is calculated by dividing the stiffness over structure mass, the Howe Truss emerged as the clear winner, providing the best balance of stiffness and weight. Finally, let us look at the suspension bridge. So it is a very light structure, approximately 1,500 kilograms, but unfortunately this structure was too flexible for this short span, and it deflected It's not seen here, but the maximum displacement is about 66 millimeters. So this teaches us that a bridge can meet strength requirements, yet fail serviceability requirements. So to conclude, this virtual laboratory demonstrates the difference between various bridge designs, as well as importance of geometry. Through this project, I was able to prove that for the given constraints, the Howe Truss is the superior engineering solution. Thank you for your attention.